Chan presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
We know that in day-to-day life, the particles are trapped in 3D boxes. That means we are dealing with the three-dimensional things. So now we will study when the particle is trapped in the 3D box, how its energy is calculated, how its wave is calculated. We know that when the particle is moving in the 3D box, the matter waves are associated with the particles, and how that matter waves are get restricted by the boundary conditions, that I will make you understand. So I am Narinder Kaur. If you want to study this topic in detail, kindly refer this book by the Chan Publishing. E-link for this book is given in the description box. So let us begin with this topic. The next topic is the particle in 3D box. Now what is the meaning of 3D? Means the particle is fixed in the three-dimensional box. So if this is a three-dimensional box, so this length is A, and this is C, and this is B, x-axis, y-axis and z-axis, and particle is trapped in this box. Now again we will apply the boundary conditions. So in this box, the potential of the particle is 0, means the potential of this particle inside this box, that will be equals to 0. Here the particle is trapped in this box, so it will never come out. This is similar to the 1D box. In the 1D box, there are the boundary, at the boundaries the potential is infinity. So same way, these are the boundaries of the particle. So at the boundaries, the potential fields by the particle is infinity, means this potential is equals to infinity at the boundaries. So this is equals to for x greater than or equals to A. Similarly, this is for y greater than or equals to B, and z greater than or equals to C. So for these boundary conditions and outside this box, potential of this material or of this particle, that will be infinity. That means the particle cannot move freely outside this box. It will never come out, and the particle will remain inside this box. Here the potential, that is 0. Here the boundary condition, that must be x lies between 0 to A, y lies between B to 0, and again z lies between C to 0. So these are the boundary conditions for the particle. Now these are the boundary conditions for the particle to remain inside this box. Now the particle remain in this box. So again, when the particle move in this box, so for the moving particle, matter waves are associated with the particle, and these matter waves which are associated with the particle, they can be represented by the wave function psi. So psi, that is a wave function which represent the matter waves. Now the solution of this matter waves, how we can find out equation for this matter waves, that can be solved by using the Schrodinger wave equation. So the Schrodinger wave equation in the 3D dimensional box, that can be written like this. So firstly we will write out the del operator. Now this is known as a del operator, which shows the variation of this wave function in 3-dimensional. This is for x-axis, y-axis and z-axis. So this is the one part of the Schrodinger wave equation which shows the variation of this matter waves which are associated with the particle in the 3D box, and this is also called del operator. So that can be written like this. So del operator, that is equals to this is called del operator, or Laplacian operator. Now the Schrodinger wave equation in 3-dimensional, that can be written like this. Now this is the Schrodinger wave equation in the 3-dimension. Now apply the boundary condition on this equation. So first boundary condition is V equals to 0 inside the box, otherwise V, that the potential, is equals to infinity. Now when potential is equals to infinity, here the second boundary condition is V equals to infinity. Now for the second boundary condition, that is V equals to infinity, when we put V equals to infinity, this wave function will become infinity. That means we are not able to define this matter waves. So that is not possible, means outside the box the material will not be present. That means the particle will not come out from this 3D-dimensional box. So we will take this V equals to 0. So substitute this value over here, then we will get, now this is a del operator. So this is known as, can be written as del square psi E into psi, that is equals to 0. So write this as equation number 1. Now this is the Schrodinger wave equation inside the box and the potential, that is equals to 0. So we are applying here boundary condition first, that is the potential is 0 inside the box. Now we want to solve this equation. Now in order to solve this equation, this psi x, y, z, that means the wave function depends upon these 3 coordinates x, y and z, that can be written as multiple of x, multiple of y and multiple of z. Means this psi x, y, z, this is a combination of x, y and z. Now substitute this value in the equation number 1, then we will get into x, y, z plus now x, y, z. So we have to differentiate this x, y, z with respect to x square, y square and z square. So this equation will become plus this factor will come as it is equals to 0. Now divide the whole equation with x, y, z. Divide this with x, y, z, then we will get on both the sides write this as equation number 3. So now you can clearly see that this depends upon x only, this part depends upon y only, this depends upon z only, and this is the constant part over here. Here E is the energy eigenvalue which contains the component of energy along x axis, y axis and z axis. That means E here, that can be written as combination of x, y and z. So again separate out the x components and x, y and z components, then we will get here, on separating the components, we will get one by x d square x by dx square plus 2m into Ex, that is equals to 0. So, write this as equation number 4. Ez, that is equals to 0. So, this is the equation number 6. Now, in the equation number 4, that depends only on the x component. So, this partial derivative of x, that can be replaced by the full derivative of x. Again, equation number 5, this contains only y component. So, here partial derivative of y, that can be replaced with the full derivative of y. Similarly, with the 6th equation, in which it contains only the z component. So, partial derivative of z, that can be replaced by the full derivative of z. So, now we have to solve this 4, 5 and 6 equations. So, these equations will become so this is the equation number 7. This is the equation number 8. This is the equation number 9 over here. Now, these equations are similar to the particle trapped in 1D box. So, these equations are solved in order to get energy eigenvalues in the 3-dimensionals and also the wave function. Now, we will take a short break over here. So, now firstly we are calculating here the particle which is trapped in the 3D box and summarize the equations in the 1D box along x-axis, y-axis and z-axis. Now, in the second part or in the after the break, we will study how the energy eigenvalues along the different axes and the wave function along the different axes.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy. Before going to break, we studied the particle trapped in the 3D box and calculate their material wave equations in the 1-dimensional, x-dimensional, y-dimensional and z-dimensional. Now, we will calculate its energy eigenvalues and energy eigenfunctions. So, the equations are E into x, that is equals to 0. Here is the Ex, Ey, So these are the three equations. That means when the particle is trapped in the box, so this is the material wave or the matter wave which is associated with the particle along x-axis. This is the wave which is associated with the particle along y-axis, and this is the wave which is associated with the particle along the z-axis. Now we have to calculate energy eigenvalues, that is Ex, Ey and Ez, and the energy eigenfunctions, that is x, y and z. In the similar way, as we solve for the particle trapped in the 1D box, we know that's a solution that can be calculated like this. Here you can put this 2m by h cross square into Ex, that is equals to kx. Now substituting this, we will get over here now solution of this equation, that will be comes like this. So here x, that will come equals to here a, that is a normalized vector along the x-axis, so that will come sine nx pi x by a. So this is the solution of wave along the x-axis. Now on normalization, we will get this a vector, that is equals to under root 2 by a. So this is a normalized vector along x-axis, because a, that is the length of the box along x-axis. So the x component, that will become over here. This we can solve similarly as by the particle trapped in 1D box. So this is the solution of the material wave along the x-axis. In the similar way, along the y-axis, we will get, now along the y-axis, the length of the box is b. So here length will come b for the normalization constant upon b. So this is the solution of the Schrodinger wave equation along the y-axis. In the similar way, along the z-axis, we will get so this is the wave function for the particle which is trapped in the 3D box along the z-axis. Now we know that the complete psi wave function x, y, z, this is equals to product of these three, x, which is a function of x only, y, this is a function of y only, and z, that is a function of z only. So this is equals to multiple of these three. Now multiply these three, we will get, so psi wave function so this is the first component into second component, that will be into third component, that will be, so this is a complete wave function associated with the particle which is trapped in the 3D box. So that is equals to under root of 8 ABC. What is ABC over here? That is the length of the cube, width of the cube and height of the cube. So ABC, it will represent volume of the cube. Now into these three components. So the complete y wave function, that can also be written as, now ABC, that is equals to volume of the cube so we can write psi wave function 8 upon V, that is the volume of the box, now this is the complete wave function for the particle trapped in the 3D box. Again, similar way, as we have been calculated the energy eigenvalues in the one-dimensional box, in the similar way energy eigenvalues for Ex, here Ex, that will becomes equals to n square. We know that that is n square pi square upon 8ma square. So this is the energy value for the particle which is trapped in the one-dimensional box. So in the similar way along x-axis, this will be equals to nx square pi square by this one. So this is the energy value, or you can say that the energy eigenvalues along x-axis. Component of the energy eigenvalues along x-axis. In a similar way, Ey, that will be equals to ny square 8m b square, and Ez, it will be equals to m into c square. So the complete value of the energy, that will be equals to Ez square under root. So this is the value of energy for the particle which is trapped in the 3D box. Now we will write it over here. So the energy, that can be written as, now in this case, pi square upon 8m. So that will be taken out. So that will be equals to here nx square Now this is the total energy eigenvalue for the particle which is trapped in the 3D box. Now what is the value of nx, ny and nz? So these are defined here, the quantum numbers. So nx, we know that clearly, it varying value from 1, 2, 3 and so on. Ny along y axis, its values again varying from 1, 2, 3 and so on. And nz, this value. So here nx, ny and nz, they are not equals to 0, because when we take this numbers equals to 0, the complete wave function will become 0. That means the wave function will vanish if we take, so this will vanish if we take this nx, ny, nz equals to 0. Means if all the n's are, if these all the n's are equals to 0, then in that case the wave function will become 0. That means there is no particle present in the box. So that's why ny, nx and nz, they are starting value from 1, 2 and 3, so on. Now on plotting these values, wave function, we will get in a similar way. So this is the wave function for the particle for n equals to 1. N equals to 1 means nx equals to 1, ny equals to 1 and nz equals to 1. So here this is the first function psi 1. Again for the psi 2, this is the wave function. Now this is the wave plotting of the wave function for the different n values. See, in the similar way, we know that the probability density current that is defined as psi into psi star. So this is defined as the probability density current, and in this space we can write the probability density function is as 0 to a, again 0 to b, 0 to c. Here x can changes its value from 0 to a, y can change its value from 0 to b, and z from 0 to c. Then psi star, dx, dy and dz, that must be equals to 1. Means the particle is trapped in the given box, and the probability of finding the particle within the given box, that is always equals to 1. That means particle must be present in the box, it will never come out. So this must be equals to 1. Now on plotting this probability density function, here we will get and that is for n equals to 2. In a similar way, so this is a psi 2, you can see that this is the probability P2, for n equals to 2 probability will be P2, and for n equals to 1 this probability will be equals to P1. So this is the value of the probability density function for defining the particle inside the given box. So these are the energy eigenvalues and the wave function values for the particle defined in 3D box. So the wave function of the particle So this is a wave function of the particle which is trapped in the 3D box. Now here the psi, it's also depend upon ny, nx, ny and nz. So that means psi, it can be written as psi n over here and nx, ny and nz. So these three quantum numbers here, they are not equals to 0, because when they become 0, sin 0 is again 0. This will also become 0 and this will also become 0. That means the wave function of the particle, it will become 0. So if this is 0, so that means now if the psi n, if this wave function becomes 0, so this implies there is no particle in the box. There is no particle in the box, and which is opposite to our first assumption, according to which we assume that particle remains inside the box and the matter waves or the material waves are associated with the particle. So for this condition or the particle to be present in the box, this wave values of the quantum numbers, they are taken to be non-zero. So this is a main condition for the wave function or for the particle to be present inside the box. Okay, now till now we have been studied the particle which is trapped in the 3D box and energy eigenvalues related to the box and energy eigenfunction related to the material to be present, and we also define the different conditions for the energy eigenvalues and the wave function and the different condition for the particles to be present inside the box. Thank you. If you want to study this topic in detail, kindly refer this book by the S. Chand Publishing. E-link for this book is given in the description box, and if you like this video, kindly like, share and subscribe, and press the bell icon for future notifications.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.